All right, in this video, we're going to talk about oxygen transport and the oxyhemoglobin dissociation curve. So to start off, let's just draw the curve, right? So we've got here, not my best drawing, but that's all right. Okay, so and on this, we have our two axes. So on the bottom, normally it's written as pressure of arterial oxygen, but it actually doesn't matter. It's the pressure of oxygen somewhere in your bloodstream, okay? And then on the y-axis, we have percent saturation. And just a reminder, when we talk about saturation, it's really what percentage of the binding spots of hemoglobin are filled with oxygen, right? So if you have 100 spots filled, or 100 spots where oxygen could bind, but only 95 of them are filled with oxygen, you would say you have 95% saturation. Okay. So the other thing to remember about this is that this actually tells us the relationship between the two ways that oxygen is carried. So the first way down here on the x-axis is this is equivalent to the plasma. Okay, so it's the partial pressure of oxygen in the arteries, but really we're talking about plasma. This is measured in millimeters of mercury. And then percent saturation tells us about how much is bound to hemoglobin. Okay, and remember, this is the important one. We carry 97% of our oxygen on hemoglobin. Okay? All right, so here's our curve. Remember, it's sigmoidal shape, something like this. So we're just going to say right here, draw our lines. We're going to say that's partial pressure of 100. And then if we just come straight across, we're going to say that's 98% saturated. Okay? That's where we're normally at. It's actually impossible really to be 100%, even though that might be what the monitors and stuff say in the hospital. Due to carbon monoxide being pretty present, carbon monoxide actually will always take up a small percentage of your binding sites, but that's not important. Okay, so there you go. Nice and simple, right? A couple of things I want to point out. So first of all, right here, is what we call the shoulder, okay? And so the shoulder is where we transition from the steep part, and so here's steep, or excuse me, this is the steep part, I can tell the difference. And then, we'll erase that, and then up here would be the flat part of the curve. As long as we are on this flat part here, basically to the right of the shoulder, having a partial pressure that's greater than about 60, life is good, okay? And I know that this is not drawn to scale, so we're just going to pretend, but we're going to say that this right here is 60, and we're going to say this right here is about 80%. Okay, obviously, terrible scale, but hopefully you get the idea. Okay, when we're on the flat part, it takes a huge change in pressure to have a huge change in saturation. But when you're on the steep part, small change in pressure, huge change in saturation. And so for those of you that are going to be an anesthesiologist or do something like that, want to do something like that, really your job while your patient is under is keep them above the shoulder. As long as you keep them above the shoulder, you can do your Sudoku or whatever it is that you're doing. Okay, so, right, so here I'll write some of that. So flat, large change in pressure, so delta is change, large change in pressure equals small change in saturation, okay? On the steep part, small change in pressure, large change in saturation, okay? And that's not great. So that's kind of the basic overview. So let's do this again. I'm going to just be better, I think, to draw a new one here. So we're going to scroll down. So I'm going to draw my curve again. So here we go. All right, much better. Okay, good. So we'll do hot pink because I like that. Okay, so we're going to say that this is my normal curve. Okay, well, I can shift this curve one of two ways. Okay, I can have what we would call a right shift. Sometimes, not often, you'll hear it called a downshift. Okay. Or, excuse me, you can have, and we'll make it green here, go ducks. Okay. Here, this would be what we call a left shift. Every once in a while, I'll see someone say it's shifted up. And I can see why, but normally that's not what we talk about. Okay. So, what does this mean? All right, well, let's just pick right here. Okay. All right, so this gives you an idea, right? And remember that on the x-axis we have pressure, on the y-axis we have saturation. Okay, so let's just talk about the left shift first. So left shift, for a given pressure, so for a given PO2, that's going to mean saturation is higher. Okay. So right shift, actually we'll just do right over here. Right, so for a right shift, for a given, that says for a given pressure, that leads to a lower saturation. Okay? So now comes the question, well, how can we shift this? How can we cause a left shift or a right shift? Now, there are 4 variables. We're only talking about 3 of them in our class. Okay, but the nice thing is, if we increase any of them, if we decrease any of them, as soon as I said that, it didn't sound right. If we decrease any of them, that's going to cause a left shift. So those variables are temperature, partial pressure of CO2, or acidity. Okay, and remember that acidity is related to pH, and so what this actually means is that if I decrease acidity, I'm increasing pH. Okay, and so unsurprisingly, if I increase temp or CO2 or acidity, which means that my pH is going down, I will have a right shift. So what does this mean? So if I have any of these 3 things, what's going to be the cause? Okay. Well, a left shift, so I'm just going to write this because one of my students came up with this. This was not me. Okay, a left shift causes a lock between oxygen and hemoglobin. In other words, they want to hook up. They want to be together forever, okay? They remind me of freshmen during freshman orientation where somebody meets somebody new and they just think they're the greatest person in the world, okay? And they're just going to hang out for the rest of forever. All right? That happened to me. It's happened to a lot of people. It's all right, so it's good, okay? Right shift. So a right shift is release. So we release oxygen from hemoglobin. Okay? Right starts with an R. Release starts with an R. Left starts with an L. Lock starts with an L. All right, the last thing that I want to talk about real quick is where do these shifts naturally occur? And really, when it comes to gas exchange, there's 2 primary locations where this occurs. One, you've got in your lungs, right? We're trying to get oxygen in, CO2 out. And then we've got it in our tissues. So we're trying to get oxygen out of our bloodstream into the tissues and CO2 out of the tissues into the bloodstream. Okay, so where do we want oxygen and hemoglobin to hook up? We want it to happen in the lungs. Hey, look at another L. Okay, so left, lock, lungs. But the environment makes it so that this can happen. Compared to your active tissue, right? And if you're not sure what I mean by that or why this happens, just think about what happens when you go running or exercise. You get hot. Why? Because of metabolism. All right, so as a result, the temperature of your muscles increases. They start to get acidic, and you start to produce more CO2. Well, guess what? That's the right shift. Sorry. Oh my gosh. That's the right shift. Okay. And so this happens in your tissues. Okay. And as a result, oxygen is released from the red blood cell into the tissues. Okay. So right shift occurs in the tissues. So let's talk about the lungs. Okay. The lungs, that's where we want oxygen to lock with hemoglobin. Well, compared to your tissues, it has relatively low temperature. It has low CO2 because you're getting rid of it, and it has low acidity. And so as a result, you've got this environment where it makes it easier for oxygen and hemoglobin to bind to each other. And so there you go. That's all we need to talk about when it comes to the oxygen transport and the oxyhemoglobin dissociation curve.